Today, the discussion of the phase transition of a pure substance and the effect of pressure on temperature, I shall try to discuss in a Clapeyron equation, and thereby I shall go to the Clausius equation, which is the extension or the restricted form of this Clapeyron equation. We all know every pure substance remains in three phases. Say pure substance remains in three phases: solid, liquid, and the vapor or gas. Moreover, one pure solid substance remains also in different crystalline forms, and this, whenever heat is applied to the solid, solid goes to liquid and liquid goes to vapor or this gas, and this one is called diffusion. This one is called fusion, or it may be called the melting of this solid, and this process is called vaporization. Vaporization from liquid to vapor. Not only that, one crystalline form may change to another crystalline form of this pure solid. Say one example is alpha sulfur to beta sulfur, or the rhombic sulfur to monoclinic sulfur. These are the phase transitions of this pure substance. And whenever let us represent this phase transition of a pure substance in a more generalized way. Say alpha, the system is changing, or the pure substance is changing from this alpha phase to beta phase. Beta phase of a pure substance. Pure substance. And the essential criteria for these two phases of a pure substance remains in equilibrium is that the free energy, molar free energy of this alpha phase is equal to molar free energy of this beta phase, and this G bar of a pure substance is called the chemical potential. So whenever the two substances remains at equilibrium, the chemical potential of the substance between the two phases will remain equilibrium. We all know whenever that is G beta bar minus G alpha bar is equal to 0. So when the difference of this molar properties of these two phases of this pure substance equal to 0, it is at equilibrium. If it becomes negative, then one phase spontaneously moves from this other phase. If this one is positive, then from reverse phase is spontaneous. So we can show this one by example in this fashion. Suppose here is a container. It is the alpha phase, and here it is a beta phase. And alpha phase, beta phase, they are remaining equilibrium. Maybe this is liquid and this is a vapor. Alpha phase represented by liquid and beta phase is the vapor. And at a given, suppose this is the pressure and this is the temperature. At this temperature pressure, these two phases are at equilibrium. Equilibrium means this one are coming in contact and moving from one phase to another phase. The rate of going from alpha phase to beta phase is equal to rate of coming from beta phase to alpha phase. These are, and the essential criteria for this one, this is the G alpha bar and this is equal to G beta bar whenever it remains at equilibrium at a given temperature pressure. So these sort of phase transitions, solid to liquid or liquid to vapor or alpha sulfur to beta sulfur, these are called the first order phase transitions. These are called the first order phase transitions. First order phase transitions. There are some criteria for this first order phase transitions. The criteria number 1 is that G alpha is equal to G beta, means free energy changes continuously from alpha phase to beta phase, and so at this transition temperature these two becomes equal. And the second one, first derivative of this free energy with respect to pressure at a given temperature is not equal to del G beta bar by del V at a constant temperature. It means that the difference of these two are not equal to 0. We can express this one. Since the first order derivative of free energy changes suddenly or discontinuously, this is why it is called the first order phase transitions. We know the basic equation, basic thermodynamic equations, basic thermodynamic equation. Basic thermodynamic equation as dG bar equal to V bar dP minus S bar dt. S bar dt. dG bar equal to V bar dP minus S bar dt. Here the bar over the symbol represents the molar property. This is the molar free energy, this is molar volume, this is molar entropy of the substance. So, actually, so this term we could write del G bar by del P at a constant temperature. Temperature is constant, this time equal to 0, so this one equal to V bar. And similarly, del G by del T at constant pressure is equal to minus S bar. So here we can represent that. Here it is V bar alpha not equal to V beta bar. V alpha bar is not equal to V beta bar. It means that whenever 1 mole of this pure substance changes its state from this alpha phase to beta phase, there is a change in volume, and this change of volume occurs discontinuously or abruptly. And we can see whenever 1 mole of liquid transits from this liquid phase to the vapor phase, there is a large change of molar volumes. And third criteria, we can also write del G alpha bar divided by del T at a constant pressure is not equal to del G beta bar divided by del T at a constant pressure. It means that the S alpha bar is not equal to S beta bar. This is also obvious that with these examples, liquid to vapor, when 1 mole of liquid is vaporized to 1 mole of this vapor, there is a large change of this degree of randomness, means the entropy of this substance increased very rapidly, very abruptly. And these 3 criteria we can show in a definite sketch. Say here is graph, here it is temperature, and it is this G bar, molar free energy is plotted against this temperature for this phase transitions from alpha to beta. So this is at a given pressure. At a given pressure, we can also keep this pressure fixed at 1 atmosphere. So this is the say transition temperature, say TB. We can illustrate with this example of this water liquid to 1 mole water vapor. If P is taken at or kept, P is kept at 1 atmosphere by our own choice, then boiling point or the transition temperature is equal to 100 degrees centigrade. However, boiling point will change with the change of pressure. So this is the transition temperature, this is the boiling point. Below the TB, below the temperature, whatever the temperature is below this TB, then it is this liquid water. And above this boiling temperature, this more stable form is the vapor water. And this is the transition temperature at which both are remaining at equilibrium. Both are remaining at equilibrium in this boiling point. So the with the rising temperature, free energy decreases, as we have shown earlier. So this one actually this and this one. So at this transition temperature, whenever at this temperature, say suppose for this case of water, whenever the pressure is 1 atmosphere, boiling point is 100 degrees centigrade. At this temperature, when 1 mole of water converts into 1 mole of vapor, in this case, whenever both are remaining equilibrium, it is G bar of this liquid is equal to G bar gas. Both will remain same. That means G changes continuously. But if we do this curve, say here is the T and here is V bar. V bar means the first order derivative of free energy with respect to pressure at constant temperature. So this one becomes, this is the transition point, here this liquid water stable, and here is vapor water stable above this boiling point, So in this case, when 1 mole of water, liquid water changing to 1 mole of vapor, say here the liquid at this temperature, only the liquid water is there. With the rising temperature, it is increasing, and whenever this water attains this temperature of a boiling point, the vaporization occurs, and the vaporization, the vapor also increases with this rising molar volume also increases. But this one actually V gas, molar volume of this gas, and this one is the molar volume of this liquid water. So there is a sudden abrupt change of this volume whenever this water changing from this liquid to vapor. So this another graph similarly, I can also write here this S bar in a similar way. It is a T, and this is the transition temperature Tv. Here this water, liquid water, and here similarly the vapor water, and this is the transition temperature. So with the rising temperature, here it is the water, only simple water, no vapors, and here is the only vapor, no liquid, and as the temperature is increased, the entropy of this liquid is increasing, and whenever it vaporizes, then its entropy becomes like that. And the curve, this curve is slightly different. Here the curvature is negative. Here the curvature is negative, means we know the del 2s divided by del t square at constant pressure is equal to minus Cp by T, and this one is negative. Means curvature is negative. So this entropy changes with the rise in temperature in this way, and here it is also in this way, not in that fashion directly. So these are the 3 criteria of this first order phase transition, and in terms of this case, it is also seen that free energy changes continuously from alpha phase to beta phase, or from liquid water to vapor water, but first derivative of free energy with respect to pressure changes discontinuously. First order derivative of free energy with this temperature at constant pressure also changes abruptly. Now I shall try to explain the here it is seen that alpha phase and beta phase, these two are at equilibrium, and so the molar free energy of these two phases is equal for this pure any pure substance, and if we change this pressure, then this T also changed. This phase rule, I can define this phase rule. Phase rule is F equal to degrees of freedom. It is the number of component, number of phase plus 2. 2 is given for this. One is for temperature and other is for this pressure. So for here component pure substance means one component. Pure substance means one component, and for one component C equal to 1 and P equal to 2 phases are there, 2, and so F equal to 1 minus 2 plus 2 equal to 1. It means that for this system, whenever two phases remains at equilibrium of a pure substance, only one temperature and pressure, only one is independent variables and other is dependent on the other. So in this case, if you keep this pressure according to your own choice, then temperature will be automatically fixed. And this is the pressure could be pressure. If it is vapor and liquid, this pressure could be determined by means of manometer, and temperature also could be determined by means of a temperature. When this temperature could also be determined by means of thermometer, and so this P and T could be plotted for this equilibrium. Shape. Here it is the T and here it is the P. Since the free energy depends on temperature and pressure, so the graph, whenever the pressure temperature is changed, the pressure is also changed, and this curve will be like this way. This curve will be like this fashion, and you see this curve is the line for the coexistence of these two phases, alpha phase, beta phase, and this one I can write coexistence curve between the two phases, and here always G alpha bar equal to G beta bar, and in this upper portion, this one is only the alpha phase, and this one is only the beta phase. So this may be called this liquid according to this diagram, and this one is the vapor or this gas. So if you keep pressure here according to your own choice, say 1 atmosphere or like that, then corresponding transition temperature is this one. If this one is P1, then this is the temperature T1 at which these two phases remain equilibrium. If you slightly change this temperature, then pressure is also changed. If it is a T2, then it is a P2. And this one is called dP, and this one is called dT. So if you change this pressure from P1 to P2, the transition temperature is also changed from T1 to T2, and whenever these two phases are at equilibrium. So actually, whenever this temperature is changed by giving, if the heat is applied to the system, this temperature will change, and whenever the temperature is changed, this vapor pressure of this liquid is also increased or changed. And if you change this temperature by dT amount, then vapor pressure will also be changed by dP amount. So this means whenever the temperature is changed, the system attains a new equilibrium, and whenever new equilibrium is established, then also the free energy is also changed, and in this case, this dG beta bar is also equal to dG alpha bar. The difference of these two will be the same. But in basic, if we apply the basic relations, then it is clear that instead of this one, we can write V beta bar into dP minus S beta bar into dt. This one equal to V alpha bar dP and minus S alpha bar and dt. These are replaced by this one according to this basic thermodynamic equation. So if we make a side change, then V beta bar minus V alpha bar into dP is equal to S beta bar minus S alpha bar into dt. So dt or say dP by dt, we can write this S beta bar minus S alpha bar divided by V beta bar minus V alpha bar. So this is the form of this Clapeyron equation. This one is called the Clapeyron equations. It is obvious that this Clapeyron equation is valid only for the first order phase transitions, where the volume changes discontinuously, entropy changes discontinuously. If these two are changing continuously, then this would be also equal to 0, and this would be also equal to 0 by 0. This equation becomes impossible. This becomes meaningless. This equation could not be developed for this if it is not the first order phase transitions. So as I can mention also, for the second order phase transitions, the first derivative changes continuously, but the second derivative of free energy changes discontinuously. As the examples I can say, the ferromagnetic to paramagnetic for this Curie point, or say liquid helium 2 to liquid helium 1 in lambda point. These are the second order phase transitions, and naturally this Clapeyron equation is not valid for this second order phase transition. And this one, so this is the dp and this is the dt, and this one, whenever 1 mole of this alpha phase converts into 1 mole of this beta phase. These are the entropy changes, these are the entropy difference, these are the entropy difference between the two phases. So this one I can write. This one I can write. This d p divided by dt. It is not a partial differentiation, it is the actual differentiation. This one equal to del S bar entropy, molar entropy change for the transitions of the alpha phase to beta phase, and this one equal to V beta bar minus V alpha bar. So this entropy change, whenever 1 mole of this alpha phase converts into 1 mole of beta phase by the applications of this heat, and this heat is the latent heat. This heat will not change this temperature whenever these two phases are at equilibrium at a constant pressure. So this entropy, molar entropy change of the pure substance in between the two phases, we can write del S bar equal to del H bar and divided by temperature. Temperature is the transition temperature at which this heat is being absorbed for 1 mole. And this one is called the molar enthalpy change. Molar enthalpy change for the substance in going from alpha phase to beta phase, or it is sometimes also called the molar latent heat of transitions. So writing this one changing this could be replaced by this one, and the Clapeyron equation becomes this del H bar and divided by T and V beta minus V alpha bar. This is the Clapeyron equation. So the sign of a Clapeyron, sign of dp by dt depends on the sign of del H bar and the difference of these two molar volumes. I can give some examples, cite some examples here. Say one example is that the vaporization of Vaporization of a liquid. Vaporization of a liquid means here it is the liquid to vapor. These two are at equilibrium. So whenever this 1 mole of liquid is vaporized to vapor, then this equation is that dp by dt equal to, this one is the molar latent heat of vaporization, or I can say this one del H bar and vaporization process, and this is the vaporization process, and T into V gas bar minus V liquid bar. So the sign of dp by dt depends on this term and this term. Here the heat is supplied to this liquid to the substance for changing this liquid to vapor, and this one is the endothermic process, and so this del H bar vaporization is equal to always positive. And this Vg bar minus Vl bar is also positive, as Vg bar is much greater than Vl bar unless this temperature is near to critical temperature. At this critical temperature, both are coming almost approaching to be equal. But much below the critical temperature, this Vg bar is always greater than Vl bar. So this one is positive, this different sorts of positive. So this one we can write this as positive. It means that if we increase this temperature, then pressure is also increased. As in the case of liquid to vapor vaporization process, if we increase this temperature, vapor pressure of the vapor pressure is also correspondingly increased. And in other words, we can show if we keep this external pressure at this P, then boiling point of this if you increase this pressure, then boiling point is also increased. As we have seen, here the pressure is 1 atmosphere and liquid boils at 100 degrees centigrade. But if we go to some hill station where the atmospheric pressure is less than 1 atmosphere, then water will boil also at lower temperature than 100 degrees centigrade. Or similarly, another example I can show, I can say here, in a pressure cooker, the superincumbent pressure is made to keep high, and so water will boil at a hard temperature. Say another example. Say example number 2. This is solid or melting of a solid. Here, suppose here it is solid. Say paraffin. One example I can give here, paraffin solid and the equilibrium with the paraffin liquid. So in this case also this relation is dp by dt equal to here delta H bar and fusion or melting, and divided by T into V L term is positive, and for most of the solids, for most of these cases, the liquid molar volume of this liquid is greater than the molar volume of this solid, and so this one is also positive, this one also positive. So this is also, this dp by dt is also positive. It means that with increase in superincumbent pressures over this liquid, over this solid, its melting point is also increased. Means whenever P is increased, the melting point or the fusion temperature is also increased. Now only one exception is that, I can put here the melting of ice. Melting of ice. And in this case, here it is ice. Here it is ice to liquid water. Ice to liquid water. And in this case, this Clapeyron equation becomes dp by dt equal to, here L or del H bar and fusion and divided by T into V, and here the liquid, molar volume of this liquid and molar volume of this solid close. So this one is positive. Positive heat is to be applied to this ice to make it water. But this, in case of this, for this system, the liquid water is more compact than the solid ice. So this one is negative. This is greater than this one. So this one is negative. And you know that the ice is having the more molar volume than this liquid, and this is why this ice floats over this liquid, and so this one becomes negative. It is the only exceptional case where with increase in temperature, if you increase this temperature, then or increase this pressure, then melting temperature is decreased. Melting temperature is decreased. This is a very common phenomenon. If you press this two pieces of ice pressed together, then at this junction there will be a pressure is high, melting point is decreased, and whenever you release this pressure, this molten water becomes again is freezed. It is freezed, and so two pieces of ice becomes one piece of ice by applying this pressure. This is a common example. So these are the three cases which are the examples of this Clapeyron equation. This is the Clapeyron equation. So I write here the Clapeyron equation as Clapeyron equation. Clapeyron equation is dp by dt equal to del H bar and divided by T into V beta bar minus V alpha bar. So this Clapeyron equation is useful, very useful in order to draw the phase diagram in a multi-component, multi-phase systems. Not only that, for derivations of this elevation of boiling point or depression of freezing point, this sort of equation is highly used. So Now I like to simplify this Clapeyron equation, and the simplification was made by Clausius in 1850. In 1850, Clausius modified in 1850 modified this Clapeyron equation. So for these two specific processes. These two specific processes, one is the solid to vapor, this is the sublimation, this is the case of sublimation, and second one, this liquid to vapor, and it is the case of vaporization. Here the molar latent heat of sublimation is sum of this molar latent heat of fusion plus molar latent heat of vaporization. So in this case, for these two cases, this Clapeyron equation could be simplified, and this simplification was made by Clausius in 1850. What are these simplifications? One approximations and one assumption have to be taken to simplify this equation to get a more handy form of this effect of pressure on this transition temperature. So this one, for this case, so we can write dp by dt equal to, this could be written as L bar sublimation, and divided by T into P bar, and this vapor gas, the solid bar. And for this case, it is dP by dt equal to L bar and vaporization, and divided by T into Vg bar minus VL bar. And you know this L is sublimation is equal to L bar, F sublimation, molar latent heat of fusion plus molar latent heat of vaporization. As the heat, whenever heat is given, the solid first melts into liquid and then it vaporizes. So in both the cases, one thing is that the Vg bar is much greater than Vs bar, or here also Vg bar is much greater than VL bar. Except whenever the temperature is not near the critical temperature. So in this case, if we consider this one specifically, then we can make an approximation. Actually, VL bar would be neglected in comparison to this Vg bar. In this case, the equation is that the dP by dt equal to Lv bar, molar latent heat of vaporization, and here T and simply the Vg bar, molar volume of this vapor. And this is the assumptions. This is the approximation. And now I take one assumptions. Assumptions is that this vapor is assumed to obey the ideal gas equation. So whenever it obeys this ideal gas equation, we can write this Vg bar or 1 molar volume of this gas according to this ideal gas equation is RT divided by P. RT by P. So replacing this one by RT by P, we get this equation L V bar divided by into P divided by T into divided by RT square. RT square. This is the more simple form than this one, but this is more accurate than this one. But this one, though it is less accurate, but it is more handy. If we do the integration, then we can see how the equation becomes very easy to handle mathematically for the effect of pressure on this transition temperature for this evaporation process or for the sublimation process. And so here side change dP by P, we make a side change and it is LV bar divided by R into dt by d square. Dt by d square. This process is called the separation of variables. So left hand side is pressure variable, right hand side is the temperature variable. And if we consider the short variations of the short range of temperature, then within this it is assumed that LV bar is independent of temperature pressure. In this case, we can do this integration and it is kept, these two kept outside of the integration. And whenever the integration is made, it is lnp, indefinite integral, and minus LV bar by R into 1 by T and plus C. C is the integration constant. So this equation gives us several features. If we draw this curve, suppose here it is lnp and here it is 1 by T, then this curve will be like this way, and this is the C. Of course, it is to be remembered that the temperature range should not be very high. For this temperature, if the temperature range is very high, then LV bar does not remain constant, and this LV bar has to be changed according to this Kirchhoff equation. So actually, if the temperature range is taken high, then this curve will not give you the linear one. So this slope of this curve equal to minus LV bar by T. So from this slope, LV bar could be calculated. This LV bar will be the average value of this temperature limit that we have taken in plotting lnp versus 1 by T. Again, you can see whenever T is increased, 1 by T is decreased, means coming in this way, then lnp is increased, means the pressure is increased. So it is already discussed. It is already discussed that with the rise in temperature, the vapor pressure of this liquid is also increased. And now, if we do here it is written separately, this lnp equal to minus LV bar by R into 1 by T plus C. if we do this integration, definite integral, if we do the definite integral, whenever this pressure is P1, temperature is T1, and pressure is P2, temperature is T2. And it is considered that between this temperature T1 and T2, LV bar remains assumed to remain a constant. And this T1 and T2 should not be the difference or the variation should not be very high. So if we do this integration, then it is ln P2 by P1, and this one will be equal to LV bar divided by R into 1 by T1 minus 1 by T2. It is the elementary mathematics by putting here. This is obtained. Or you can say this ln P2 by P1 equal to LV bar by R into T2 minus T1 divided by T1 T2. This equation is very simple to calculate the effect of pressures on this transition temperatures. If you know this molar latent heat of evaporation of this liquid and also know the transition temperature at this pressure P1, then you can calculate this transition temperature at T2 at this pressure at P2. So this is a very useful equation. Not only that, if you know the transition temperature T1 at this vapor pressure P1, transition temperature T2 at this vapor pressure P2, then you can also calculate the LV bar. If you know this T1 at this T1, suppose you know the vapor pressure P1 at this temperature T2, vapor pressure P2, then LV bar could be calculated within the range T1 to T2. It will give you the average value. And you can see very interestingly this, you can remember this for the vent of isobar, or right side by side, vent of isobar, in chemical equilibrium, and this one is the ln Kp2 divided by Kp1 is equal to del H bar by R into T2 minus T1 divided by T1 T2. These two, these two are the equilibrium constant in terms of these partial pressures, and this one is the enthalpy, molar enthalpy of these chemical reactions, and it is very clear these two are not only similar in external features, they are also similar in their internal content. Here Kp2, here P2, Kp1, P1, and delta H bar, LV bar, and these are the temperatures. And so this is the special case of this one. And if you try, then this equation you could derive from this one. Whenever this liquid and vapor remaining at equilibrium. Then another feature is that from this equation I can frame up one rule, and this rule is the Trouton rule. Trouton's rule. From this equation. And whenever this P equal to 1 atmosphere, if you take this pressure, if you keep this pressure at 1 atmosphere, then T is equal to this TB, and TB is called the normal boiling point. Normal boiling point. Normal boiling point. It is clear that the liquid is not having a particular boiling point. This boiling point depends on the external pressure, the superincumbent pressures. If the superincumbent pressure is kept at 1 atmosphere, then this liquid boils the temperature, and that temperature we call the normal boiling point, or sometimes also called the standard boiling point. So if we put these two conditions here, then ln1 equal to 0 and 0 equal to minus LV bar by R into 1 by T plus C. Or I can write this LV bar by TB, here it is TB, normal boiling point, and TB, and this one equal to RC. This R coming here, RC, and RC is also a constant. Means a ratio, means a ratio of this molar latent heat of evaporation with its boiling point. This ratio is constant for this liquid. Only the limitation is that this relation is valid only for this simple and non-associated liquids like liquid benzene, liquid toluene, liquid carbon disulfide, liquid chloroform, or say cyclohexane, etc. So for water, this will be a little bit higher than this constant. If we do the calculations for the simple and non-associated liquids, then this one will be found to be 21 calorie mole inverse and Kelvin inverse. So this heat change occurs at a constant temperature, and that temperature is a TB. Whatever the pressure is 1 atmosphere. So this one is the entropy, molar entropy change of this evaporation at a normal boiling point. And this one equal to 21 calorie mole inverse and Kelvin inverse. For this, for simple and non-associated liquid. But for the case of water, this value is about 26 calorie mole inverse Kelvin inverse, as water is associated liquids, and so some amount of heat is first required to dissociate the water molecules. Waters are remaining associated due to the hydrogen bonding, and next this water molecules are to be vaporized. So more amount of heat is required. So from this, one utility is that from this value, LV bar could also be calculated approximately. LV bar could also be calculated as 21 into TB. This is also one application of this Trouton's rule. Trouton's rule is more general for the simple and non-associated liquids, and this is all about the first order phase transitions, Clapeyron equations, and how the Clapeyron equation is modified for these two cases and Clausius equations, and then again coming to this Trouton rules. And I now give one example here, or say one problem. Say problem is that problem, very simple problem. Say rate of change of pressure, rate of change of vapor pressure, with respect to temperature of water around 100 degree centigrade is 2.7 centimeter of mercury per degree centigrade. Now the calculate the boiling point of water at 75 centimeter of mercury. This is a very common question, very simple. This rate of change of vapor pressure means dP by dt. This dP by dt is equal to 2.7 centimeter of mercury per degree centigrade around 100 degree centigrade. From this graph, it is very popular. Here is P and here it is P, here T. This curve is like that. The curve is like that, and so this is the slope of this curve. This is slope of this curve, and slope of this curve is changing with this temperature. Here the temperature slope. This is the tangent. This is the tangent. At this point, if you would like to calculate, then this one is the dP by dt. Here it is at this temperature. It is the dP dt. So dP by dt is temperature dependent, tangent temperature dependent. So around 100 degrees centigrade, this one having this value. Means with this 2.7 centimeter of mercury pressure to be given access to increase the tension temperature or the boiling point by 1 degree. 1 degree centigrade. If you try to raise the boiling point by 1 degree centigrade, then the external pressure or the supernumerary pressure is to be changed to 2.7 centimeter of mercury. These calculations could be easily done by assuming that whatever the pressure is 1 atmosphere, means 76 centimeter of mercury, when pressure is equal to 76 centimeter of mercury, then boiling point is equal to 100 degree centigrade for water. This is known to us. So this dP means P2 by P1, and here P2 by P1, and this one equal to 2.7 centimeter of mercury per degree. So if we substitute 76 for P2, then 76, and here P1 75. Whenever the pressure is 75 centimeter of mercury, we like to calculate the boiling point. And so it is the 100 degree and minus it is the T1 and suppose T degree centigrade, and this one is equal to 2.7 centimeter of mercury per degree. So if we do the calculations and then T will be equal to 99.63 degree centigrade. And the Kelvin's difference of Kelvin scale of temperature is equal to the difference of this degree centigrade scale, and so it would be, instead of this one we can write this one, no problem. So boiling point of water at 75 centimeter of mercury is 99.63 degrees centigrade. This is all about today's discussion, and I have illustrated the first order phase transitions and the Clapeyron equations and the extension or the modifications of the Clapeyron equation is the Clausius equation, and then I have framed up one Trouton's rule and one problem has also been given to illustrate this subject matter. So thank you all who are watching this video. If you like, then please subscribe and encourage me to do more video about this subject matter, and this certainly I think will be helpful for especially for the chemistry student. Thank you all.